Hello, my dear students, and welcome to the third and penultimate discussion of our topics in Chapter 4, the discussion of reactions that occur in water in aqueous solution, and one group of reactions that occur are oxidation reduction reactions. This will be discussed in much greater detail in second semester chemistry, where we discuss a topic called electrochemistry, kind of related to plating. This was one of my first introductions to chemistry in high school, and in community college, I actually worked at a plating shop, plating aircraft parts for Turbine Support Division of Chromalloy America. But what we're talking about is moving and pushing electrons around. In a reaction, we make and break bonds, and those bonds are electrons that have been transferred to form ionic bonds, or electrons that are shared to form covalent bonds. And a lot of times, reactions get classified in other ways as well. So you can have a redox reaction that is also, for example, a double displacement reaction or something. So there are some of these categories overlap, is my point. Now, if you lose electrons, that is an oxidation. And if you gain electrons, that is a reduction. So before I go on, let me please give you what I always found handy. I still kind of go grr once in a while to make sure I'm saying the right thing, because it's, at least in the beginning, easy to get confused. I was taught Leo goes grr. And the way this works is, if I can go back to Ridge Runner Red, loss of electrons is oxidation, Leo the lion, and he goes grr. Gain of electrons is reduction. I'm ashamed to say it was a high school chemistry teacher after I'd already retired from the university who taught me this one in Arkansas. As a good Texan and a good Texas chemist, I should have known this. Perhaps even easier is oil rig. Oxidation is loss. Oxidation is loss. Reduction is gain. Gain of electrons is reduction. Reduction. Oil rig. Just remember oil rig. Now, we'll talk about how we can tell if something's gained or lost electrons, but the thing I want you to remember is that an electron has a -1 charge, okay? So if something loses or gains electrons, its charge is going to change. So that's really what we're going to be talking about. Now, here's another thing I hear a lot people say. For example, you can say when you see that rusty iron, the iron is oxidized or, it's undergone an oxidation, but you can't say that's an oxidation reaction because you cannot have one without another. So here comes my UPS guy. You'll hear my doorbell. Now, the oxidation and loss of electrons, if you lose an electron, that electron has to go somewhere. So if somebody's oxidized, somebody's going to be reduced. End of discussion. If you have an electron, a free electron in the air, I guess it'd be a spark. If you have it in something conducting, an electrolyte solution or a wire or something, then it's a current, okay? You can't have free electrons, Okay, they're going to go somewhere. They're going to go to ground or to a place that attracts them in the chemical sense, an electronegative atom, or the most electronegative atom available. So these are best referred to as oxidation reduction reactions, because you can't have a reduction reaction without an oxidation reaction, because if this guy gained electrons, he had to get them from somewhere. Okay? Now, I guess you could have an oxidation reaction separated from a reduction reaction. We're going to do that in something called half cells when we create galvanic and voltaic cells to study electrochemistry and this in more detail as you go on in your chemistry, but not today and not now. So, and even though we call them oxidation reduction reactions, we change the order and call them redox reactions for short. I like this term because it immediately implies that you have both reduction and oxidation occurring at the same time. I don't know why we don't call them reduction oxidation up here, but or why we don't call them oxred down here, but these are called redox reactions. Reduction and oxidation going together. And here's a good example. Calcium metal in the presence of oxygen. And if you've ever seen calcium turnings, calcium metal, that's kind of a soft metal, kind of cool, but when you open up the jar, it doesn't look shiny and silver like a metal. It looks kind of white inside. And that's because it has, if I may, absorbed some oxygen from the air and formed calcium oxide. Calcium loses electrons. Oxygen gains those electrons. If you gain those electrons, you get what? I can't use my pen in this state. But you get more negative, and when the calcium lost those electrons, it got more positive. Ca2 plus and O2 minus form calcium oxide, which is a powdery white substance that forms on the outside of your calcium metal. So, a very common thing to happen in the lab. So let's go through and quickly look at some rules that tell us if an oxidation has occurred. And one way to tell, the for sure way to tell, is to look at the charge on every atom in your reaction, every atom in your compounds. And there's some rules for assigning what we call an oxidation number, which is a reflection of the number of atoms in some number of electrons. So in a reaction, if your oxidation number changes, it changes because you gained or lost electrons. I probably won't have you do this on a test. When we move on to electrochemistry, it may be a little bit more important, but this is a good way to tell if reactions changed and if it's an oxidation reduction reaction. So we're going to assign an oxidation number to every single element or atom in a compound, and not in a compound, but in a species. And if I may stop going in and out, elements in their elemental form, for example, iron. Okay, it is fully reduced. Means it's gained all the electrons it's going to gain, and it has a oxidation number of 0. In your elemental form, you're going to have an oxidation number of 0. Also, if you have, for example, a species like sodium +1, or calcium 2+, or let's go back to iron 3+, what's a 4+, chromium, cobalt, lead, Pb 4+. If you have species like these, their oxidation number is their charge. 4 plus, 3 plus, 2 plus, 1 plus. Also, 2 minus for oxygen comes to mind. Fluorine, minus 1. We usually just write F minus, Cl minus. Those are all minus 1, okay? Their oxidation number is the same as its charge, okay? N3 minus, so nitrogen's 3 minus. And most commonly it is, until they start forming oxyanions or complex compounds. Excuse the call from my wife, but I'm going to see if I can cancel this call. There we go. I don't know why my speaker picked it up and overdid it when I had it off. So, moving on with oxidation numbers. Nonmetals tend to have, and let me turn my phone off so that doesn't happen again, because very frequently people who call me, I hate this new iPhone 14.
Check it out.
There we go. No, Siri, I'm not going to check it out. Okay, phone is off. Continuing on, okay? If you have an element, your elemental form is always an oxidation number of 0. If you have an ion, cation, positively charged cation, or negatively charged anion, its oxidation number is the same as its charge. Nonmetals tend to be negative, and if I use the Flynn Scientific Periodic Table of the Elements, it has their most common valence or oxidation number up there. We like to say that oxygen always is minus 2. I will say it always is for whatever problems I give you. However, in the peroxide ion, which is a very reactive and interesting species, has an oxidation number of minus 1. Hydrogen, when it's a hydride, is minus 1. But for almost all purposes, it's going to be plus 1. Okay, so oxygen is, don't forget it's usually written, the ion is 2 minus, O2 minus, and hydrogen is most frequently like that. So this is always a minus 2, and this is always a plus 1, with notable exceptions. So we had, going back, elemental forms with a valence oxidation number of 0. Gold, let's use my favorite one, pure gold. It's totally reduced, and it has a oxidation number of 0. Any pure element does. Even oxygen in its atomic molecular oxygen form. So, nonmetals tend to have negative ones. Metals tend to have positive ones. Fluorine always has a minus 1, and most of the other halogens do too, but not when they form, for example, oxyanions, most notably like sulfate or phosphate or sulfite. So those, to get to this charge and to obey the rule that the oxygen is always minus 4, gives these, for example, positive numbers. We're not going to spend a lot of time on this, but in a neutral compound, those oxidation numbers of all the elements, all the atoms in that species, add up to 0. And if we're talking about a charged species like this phosphate here, the oxidation numbers have to add up, for example, in phosphate, to minus 3. Okay, so the polyatomic ion has to be the charge on the ion. just when we cover this at some future date, I'm going to say remember back when. Here's what I like about oxidation reduction reactions. People always ask me, what happens if I mix this or mix that? Or what happens if I put this into this solution? And you'll see me, before I answer, frequently looking up in the classroom to a table called the activity series. And it will also have voltages and some other values on it that we can use in electrochemistry. But what they want to know is, if I drop this copper wire here into acid, will it dissolve? Or if I mix it in this solution, what will happen? Well, if I take some copper wire and put it into a solution of silver nitrate, the nitrate doesn't react. But in this case, I guess they use silver nitrate, and they put copper in there. And in the end, the silver, which is Ag+, is going to lose an electron. And it's going to gain an electron. See, you got to be careful. And the copper is going to lose electrons. It's going to give up its electrons. It's in its fully reduced elemental form. It's going to give up those electrons to this silver. It's going to form these beautiful, if I may, that wasn't what I wanted to do. It's going to form these beautiful needles, silver, almost crystalline silver, that are absolutely beautiful. These don't look that beautiful, but I've seen them form long, thin, beautiful needles of silver. You can kind of see it happening down at the bottom of the tube. And if you shake that copper wire off, you will see pure silver, elemental silver, fall to the bottom of the tube. The other thing you'll notice is that the solution is turned blue, because as the copper gave up its electrons. It's a metal. Most solid metals, are, according to the metallic structure, floating, their nuclei floating in a sea of electrons. They have plenty of electrons. They're frequently happy to give them up, and it gives them up, in this case, to another metal, silver. And that silver ion becomes elemental silver, becomes reduced. This is from the old terminology. It comes reduced to its most elemental form. This is from the days of alchemy. But the copper becomes oxidized, loss of electrons, oil rig, and the +2 ion, that species in solution, is blue. And there's your blue solution, blue copper ions in solution. Okay. It's not copper colored, it's blue colored. The silver, of course, is silver colored. It's colorless here because it's dissolved. And then it's silver when it becomes reduced. The reverse reaction does not occur. If I took a silver wire and put it into a solution of copper, it's basically what you have in this third tube, do I get copper metal? I can make copper using, I can take a copper sulfate solution of aluminum and make copper metal, but I'll show you why or why not. It relates to this activity series. Elements that are higher are more likely to be ions. Okay? The higher up you are, the more reactive you are. Potassium, we know what happens with potassium when we put it into water. Same with sodium. You may have even seen lithium or some of the others go into water. Calcium forms little bubbles and reacts with water. And notice down here, here's hydrogen. And if I also want to show you my copper and my silver. Copper is above silver. Okay? It's above silver. so it's more likely to exist as an ion. Copper will replace silver in solution because it's higher, but silver won't. This is called the activity series, and it allows you to make predictions. That's such a valuable skill in chemistry as it is in life. Notice, if I'm going to have an acid, what am I going to have? H plus around. So which metals react with acid? Lead, tin, nickel, cobalt, chromium, zinc, manganese. Notice I said I can take an aluminum can, soda can. So this was Coca-Cola. There's the wave. This, and I can scratch the plastic off the inside. You may not know this, but they're coated with plastic. But if I add a copper solution to it, you can see the can dissolve and solid copper precipitate out because aluminum is higher, is more reactive, and it's more likely to exist as an ion. The aluminum metal with an oxidation of 0 will donate 3 electrons to become the aluminum ion. Of course, copper can be +1 or +2. In this case, it's +2. To balance the equation, I'd need 2 aluminums and 3 coppers, but copper can pick up these electrons. The copper solution that I put in there, and the copper, 2+, can pick up 2 electrons, +2 electrons. I know 3 were made down there. I'm not balancing this, to become copper metal, Cu0. The 0 just added for understanding. So I go from an aqueous species to a solid species. This one was aqueous down here because it's an ion. My point is if you're higher on the chart, you're more likely, you're more reactive, and you will react with the things underneath you. People ask me, what would happen if I drop my ring into this acid? They must not like the ring or whoever gave it to them. But, my point is nothing will happen because gold is lower. Okay, so this is going to stay as an ion, and this is going to stay as a metal. Also with copper and silver. We're not supposed to use it with mercury. I would love to do some experiments with platinum and gold. They're pretty resistant to metals. Lead. Ask the people about what's happening in Flint, Michigan, where the lead pipes had lead salts around them. It's not really the lead metal itself, but the lead salts were dissolved when the pH dropped, when they used cheaper water that had just a slightly lower pH. And they knew damn well what they were doing, and they were criminal. And they hurt a lot of people when they did it. They should have taken my chemistry class. They poisoned people with lead. It's awful what they did. But we don't work with lead. We tried not to work with lead if we can avoid it. But there are quick and easy ways to inspect this to see if something will react and will oxidize or reduce something else. So, in our reaction, the copper reduced the silver because it was more likely to exist as an ion. So the solid copper reduced our silver, and in return, it became oxidized because you can't reduce something without oxidizing something else. A lot of times when I want to make a gas, especially hydrogen gas, and by the way, forget this doesn't go with this. That's a typo from the publisher. I just noticed that. If I take zinc metal and I add it to acid, okay, I will oxidize it to zinc 2 plus 2Cl minus I'll make zinc chloride. Plus, look what else I get. Don't forget those hydrogens. H2 gas. So a metal that is dissolved in an acid, as long as it's, if I can go back, one of the ones above hydrogen. Okay, I like to use zinc because it's cheap, plentiful, and doesn't cost me a lot, and is easier to work with than iron. It doesn't oxidize so much in air. I don't have that reaction down here, but anyway, zinc, any of these metals, so cobalt, nickel, tin, lead, aluminum, if you put them into acid, you will produce hydrogen gas. Can't do that with copper, silver, gold, or platinum, but I don't know why you would want to. That would be a very expensive batch of hydrogen gas. So this is a typical reaction of an acid with a metal to produce hydrogen gas, and that is it for our oxidation reduction. This reaction with the acid is, see, it got more positive, it lost electrons. This is my problem that people have in going from zinc to zinc ions. I got more positive, I had to lose electrons, but I lost something negative, so that's why I got more positive. You know, where did they go? Well, the Cl minus is always Cl minus, right? Because that was part of our rules for assigning oxidation states, and it's still Cl minus. But remember, the H starts out as H plus, unless it's in its elemental form, and hydrogen is a diatomic gas now in its elemental form, so this is H0. To go from a plus 1 to a 0, and there's 2 of them there, so I need 2, but I need to get more negative. I need these electrons. Those electrons went from zinc to the hydrogen. That's a pretty complex explanation of what happens in this reaction. And yet, if you very carefully think about the oxidation state and who's gaining and who's losing electrons, who's being oxidized, who's being reduced, hydrogen is being reduced, zinc is being oxidized, oxidation is loss, reduction is gain, then you can slowly, carefully work these out. But I'm not going to do too much more with this. I have a few problems for you to work, and then we're on to something very important, and that is solution chemistry. So until then, I will shut down our